We are honored today to present our paper entitled Machine Learning for Optimized Buildings Morphosis. The term morphosis is derived from the same Greek term, and it is defined by Mr. Ben Saucy as the action to give form to. And we mean by building morphosis the shape design of the building according to different qualitative or quantitative criteria. In our research we start from the following observation. Currently, developing countries are faced to rapid urbanization. The urban population of these countries is projected to double in 2030 and the built-up area to triple. This involves the construction of large volumes of new buildings which not only wastes land, increases energy consumption, but also increases greenhouse gas emissions. Thus, to face these problems and to deal with sustainable development challenges, it is important to act on early design decisions, particularly by designing a suitable building morphology. Designing built forms in urban areas is important because the neighborhood building blocks are interdependent. Particularly, energy demands over the whole year can be influenced by summer shading effects and winter solar access availability. This complex issue still does not have a satisfying solution. Its resolution would be a lever to meet climate and environmental challenges in architectural design. On the other hand, tools and methods of computational design used by architects are constantly evolving with the ability to solve complex problems and to account for a high number of variables. From now on they become crucial elements for accompanying the design process, especially with the necessity to cope with environmental challenges. Recently, machine learning has emerged and it is considered for many authors as an underway revolution. Machine learning begins to be applied in the architectural field and has evinced its potential to improve building performance. In this paper, we try to review how machine learning has been used for building morphosis at the early design stage. We then forecast the use of machine learning for optimized building morphosis in order to ensure summer shading and winter solar access between neighbors. Machine learning applications occur throughout the building design stages. The increasing number of research papers using this technique attests that it might have a broad impact on architectural practices. We propose to summarize these in three different aspects: visualization, simulation, and morphosis. Current literature used ML techniques to enhance the production of images and 3D models representation and labeling. In the field of building design, ML is used for plan generation by converting the rasterized floor plan image onto vector graphics representation. We can mention other applications of machine learning with the ability to produce 3D building representation. 3D representation can be used for style transfer as a primary material for mapping and reproducing a style. The machine learning technique has evinced its potential in simulation and prediction. Neto and Fiorelli found that ML-based energy consumption forecasting can yield better prediction results when compared with simulation software prediction results. Graham and Al presented a review of ML used to predict thermal comfort. He argues the evidence, arising from several studies and experiments, the potential and benefits of machine learning algorithms for forecasting occupant thermal comfort compared with traditional methods. The machine learning-based methodology presented by Gabakis and Al demonstrated that the urban heat island intensity can be predicted quite accurately even when using a limited set of data. In this paper, we focus on the use of machine learning for building morphosis. The machine learning technique is used to treat personal designer preferences, specific architectural styles, functional or environmental performance criteria. Christian Schoberg et al. Used ML for the formation of criteria based on the patterns learned from the user's design choices meeting their personal aesthetic and qualitative criteria. The ML-based method provided more design possibilities than a human designer and identified additional high-performing regions of the solution space based on the user's inexplicit qualitative criteria. Zhang proposes a method to quantify the design preference of shapes and find the shape with the highest score based on the result of the preference test from the architect. Newton explored machine learning to generate 3D building massing models relating to a specific urban and stylistic movement in the history of architecture. This research demonstrated that ML could serve as an analytical tool capable of revealing hidden patterns and principles of an architectural style which could be used to produce new specific designs. Evinced and presented a building function-driven approach to generate new designs. The researcher used ML to evaluate existing designs encoded as graphs and subgraphs and to merge them into a new functional composition. Machine learning is used to analyze a reference building design, with the aim of identifying the optimal solution regarding its energy or environmental performance. Chang and al. proposes a new methodology applying a generative design approach using a reinforcement learning algorithm, a parametric performance modeling to identify relationships between design parameters and urban performance. Fend and al. proposed an alternative approach, involving integration of parametric design technology and machine learning algorithms to quantify environmental uncertainties associated with early design decisions. Thus, across this review, we noticed that no ML application was found for optimized building morphosis ensuring summer shading and winter solar access taking into account the complex morphological relationships between neighbors. Although the impacts of built forms on energy performance have been considered in earlier researches, the interactive and complex relationships among neighboring have not been studied with artificial intelligence approaches. Across this review, we try to pick up how machine learning has been used for this purpose with a focus on used ML models and data generation methods. Regarding the ML models, the most common ones are artificial neural networks. With ANN, the complicated algorithm design is replaced by a learning based on a provided dataset. Nevertheless, ANN is criticized for its opacity since the correlation of inputs and outcomes is unclear. Deep neural networks are considered as a technique that revolutionized classification and image recognition tasks and even surpassed human vision. Then generative adversarial networks are used to recombine them into new designs. GANs are typically used to generate 2D and 3D designs. The GANs-based method is used to produce unforeseen designs that may have not arisen to human architects. However, GANs may require significant computational resources and time while it can be an affordable technique for architects without any coding experience. For the application of machine learning, designers must use large datasets which may not be easy to find as the application of ML is still in its beginning in the architectural field. To deal with this problem, designers can collect data from publicly available datasets, parametric design tools, building information models or IoT wireless technologies. Genetic algorithms are the most widespread type of multi-objective optimization methods. Therefore, they are also becoming a common data generation method in the field of architectural design. This review provides a basis for the machine learning exploitation in the climatic optimized building morphosis ensuring shading and solar access. We noticed that parametric tools are widely used by designers for the dataset generation. They are affordable by architects as they allow them to compose algorithms with visual scripting techniques. We hypothesized that parametric tools could offer a technique for morphotic data sourcing with possibilities to generate solutions and to perform simulations based on physical parameters of the environment such as solar radiation. ML could learn morphological parameters from designs imposed by the complexity of interaction between neighbors. Then a generative adversarial network could be used to recombine them into new designs. In this paper, we present several alternatives for the use of ML in building design, especially in the building visualization, simulation and morphosis. Across this review, we argue that the ML technique could be an interesting technique for the building morphosis. ML could enlarge the solution space with the opportunities to discover new, unexpected spatial forms and combinations. ML enables also higher efficiency in complex shape design and can respond to a vast number of parameters and relationships influencing design. This is done with relatively simple algorithms easily understandable by architects. Finally, when developing this review we noticed that despite the growth of machine learning usage, it is still limited in the field of architecture for building morphosis. We think that the ML technique should be introduced in the field of architectural design and its teaching. We argue that architects should adopt it, master it, and take full advantage of it. Similarly, they shifted in the past from manual drawing to computer-aided design and more recently to parametric design. Now, the future step is data-driven design and artificial intelligence. Thank you for your attention.